Hey, my wonderful AP students. Sign for rotation, circular motion, pendulums part. We have had one subtopic so far, gravitation. We're about to add our second, pendulums. And the idea is we're going to have a ball and a string that's released from some angle and goes down, comes back up, swings back and forth, back and forth, back and forth. It usually happens for small angles. We usually call it the small angle approximation, where sine theta equals theta, or approximately. That's usually around 10 degrees or less. So if you have a much bigger angle than 10 degrees, the period and energy stuff I'm teaching you is not necessarily going to work. So to help understand and to teach you, I'm going to go back to something we kind of know, and that's springs. We're about to make a big table. On the left, you're going to see what we're talking about. In the middle column, we're going to talk about what it means for springs, and the right, a pendulum. So, oscillates. Springs go back and forth in a straight line. Pendulums oscillate back and forth in a circular arc. What's the oscillation due to? In springs, we're going to say the oscillation is due to the spring force, a restoring force. That's negative kx. In a pendulum, that force has got to pull it down, and as it's going up, it's got to pull it back down. So, we need some kind of force due to weight, but also depends on the angle. So the restoring force, like in things on a ramp, we're going to have mg sine theta is the part of the weight that's making it go down. And that is the restoring force. For the picture, you can see we have the spring going back and forth, and here we have the pendulum with length L and angle theta. And like on a ramp, the weight downhill is going to change along with the angle. And at the bottom, you're going to have no angle, thus you're going to have no weight restoring. Thus, an equilibrium point. In a spring where x is 0, it's an equilibrium point. There's no force, there's no acceleration, there's no spring energy, and the kinetic energy is at maximum. At the equilibrium point for a pendulum, which is right as it's underneath its bob, which means there's no angle, the acceleration is also 0. There's no restoring force. There's no there's no gravitational potential energy, and the kinetic energy is a maximum. Remember the video from last time where we said how displacement in linear or translational terms is equal to angles for rotational things? This is the idea. At the max extension, when the spring is furthest from equilibrium, we have the most x distance, we have the most acceleration because of the most force, we have the most energy in the spring, and we have no velocity or kinetic energy. At the max extension here, which is when it's at its highest point, the angles are the biggest. You also have the most acceleration due to the restoring force. You have the most gravitational potential energy, and you have no kinetic energy. You might be thinking, isn't the acceleration always 9.8 or 10 or whatever, gravity downward? No, because since there's a tension here, the tension is going to have some effect on it. And you can imagine, as you're going up, the tension goes down, so there's more and more kind of weight allowing it to move. And for the period, which you know is the time for one complete oscillation, in a spring, the period is 2 pi square root of m over k. Pendulums, it's 2 pi square root L over g, where L is length of string and g is local gravitational field. So they're very similar. I haven't talked anything about the rotational part of it yet, but yet these are things you have to know and you will know. So here's my picture again. I chose 3 points, A, B, and C. A and C should be at the same height. So that means that A and C are both the maximum heights, or the maximum angles. Point B is at its lowest point, an angle of 0. So at the bottom, there's no restoring force. The tangential acceleration is 0, which means the kind of forward acceleration is 0, which makes complete sense because if it's at the bottom of its arc, that means it's moving horizontally, and you know that weight has no horizontal acceleration. The potential energy is 0, which is gravitational, and the velocity and kinetic energy are maximum. However, since it's rotating, we must also look at this with a circular motion viewpoint, not just a simple, straightforward viewpoint. There is a centripetal acceleration at every point. There's got to be. It also won't go in a circle. It will just go in a straight line. So at points A, B, C, and every single point on here, there is a centripetal acceleration. And although the acceleration tangential or linear is a max at A and a minimum at B, the centripetal acceleration is a maximum at B and a minimum at A. Since centripetal acceleration is v squared over r, and velocity is the biggest at point B, and the radius is always the same. In fact, the radius is the length. We can say that at point B, where it's going the fastest, it's going to have the most centripetal acceleration. Now it's time to talk about energy. There are two forms of energy at work here. There's gravitational, kinetic, and then combined it's called mechanical. Just like with springs, at point A, where it ain't moving, all the energy is potential, black line. No energy is kinetic, green line. And they do a cosine squared and sine squared relationship, where they constantly go back and forth. At point B, gravitational goes to 0, kinetic goes to a maximum. But if you add up the two terms, you get the same consistent mechanical energy. This is an isolated system. So at the maximum points, A and C, you have maximum potential energy. At the minimum points of height, which is B, you have the max kinetic energy. Easy to understand. Same picture. Now we're going to do the three kinds of graphs. But before I do, here's what we're going to do. We're going to call the bottom position, or B, 0. We're going to say that left is negative, right is positive. And just kind of so you know, at the angle theta of string length L, the distance it is from the 0 point is this dx. That's a straightforward distance. We're not actually going to do the arc length. So I'm going to say that the max distance is L sine theta. And you can see that in my example from over here. So for position, it can go max L sine theta backward and forward. If you're starting at point A, it is backward L sine theta. At point B, the position is 0. At C, it's positive L sine theta. So you can see how it does this sine or cosine graph, depending on how you look at it, that oscillates every period. You can see that the period goes from C to C. That's one full oscillation, from C back to A, back to C. Or it's from B through B again, back to B. From B, back through, and back. So it works out okay. For the velocity, same idea, except at point A, we look. What's happening at point A? Is it going fast or slow? Well, in fact, it's 0. And as it's going forward, it is gaining positive speed because right is positive. So it's going from a negative, it's going from 0 through positive, keeps on going positive, but it's decreasing. So from A to B, it's getting faster. From B to C, it's still positive, but it's getting slower. At C, it's 0. And again, I wrote that because it's heading to the right. Then from C to B, it's getting faster negatively, boop, boop, till it reaches the maximum at B. And then from B to A, it's getting slower negatively, heads back to 0, and repeats again. So we have, it's kind of drawn badly, I'm sorry. We have that same kind of sine or cosine relationship here. And as for the acceleration or force, again, this is tangential, not centripetal. At point A, the force is a maximum, and it's also direct to the right because it's restoring. Let's go back to equilibrium. So it starts off positive, and as it's dropping, it's getting towards 0 because at B, the force and acceleration is 0. Starts off positive, goes to 0. Then from B to C, it's moving up, but the force wants to go back to B, so the force is left, and left is negative. We can see this same approach. You can also do the method I taught you with springs in terms of finding the slopes of the graph. Your choice. Know them both. Question for you. If at some angle, say 5 degrees, you find the period is t, what would the period be if you let it go at 2 theta, or 10 degrees? Would it be twice the period, same period, half the period, square root of 2 period, or 1 over square root of 2, which is root 2 over 2 period? Can you please pause, think, and get ready? All right, welcome back. We're going to say it's B. It's the same. Only length and gravity affect it. Like a spring, no matter how much you pull it back, which is amplitude or x for a spring, theta or distance for a pendulum, the period won't change. Neither will change in the mass on the end of it, which is kind of different from a spring to a pendulum. A spring, the mass has an effect. In a pendulum, it doesn't. And that's because both forms of energy in pendulums, gravitational potential and kinetic, have mass in there, whereas for springs, only one of the equations does, so mass still has an effect. So, will doubling the angle affect the tension? Pause, just think about it for like about 30 seconds and play it again. Yeah, absolutely. At the bottom, we're going to have weight down and tension up, and there's an imbalance. There has to be an imbalance because there has to be a centripetal imbalance to keep it circular. If these two were equal, it would go straight forward and thus fall and no longer go in a circle. A bigger or higher angle means there's a higher start point. It means you're starting it up higher off the ground. which means you have more gravitational potential, which means you'll have more kinetic energy because the gravitational will be turned to kinetic. And if you have more kinetic, that means you'll be going faster at the bottom. And since acceleration is v squared over r, more velocity means you need more inward force to get it to curve. I'm going to say that again because it's so dang important. It's not just knowing the equations, understanding what's going on. If you're going faster at the bottom, you need more of an upward force to make you curve, because more velocity means you have to have more force to actually get you to change what you're doing. If you did an equation, t minus weight equals mv squared over r, upward positive plus negative equals the imbalance. The weight is fixed, so the faster you go, the more imbalance you need, and since this is fixed, it means you have more tension. So, higher angle means you're going faster, faster means you need more tension to make it. If you don't have enough tension, the string snaps, it falls. And with that, wonderful students, it's been a good evening. Take care, learn, come to class.